Okay, oh, that went quiet very quickly. Hi, good morning, everyone. Welcome to the IvS seminar series. Today we have Reinhold, who is, everyone should know, is postdoctoral researcher here at IvS. Reinhold has a bit of an unusual path into astronomy, I think. He will say that himself. He did his bachelor, somewhere in the US. No, in Canada.
Canada, yeah.
Canada. I can't remember where now.
US light.
Yeah. In Canada, then took a pause and then did his PhD directly after his bachelor in Australia, and then has now moved here to do his postdoc. And today he's going to talk about his work on black hole natal kicks.
That's right. Thank you, Rose. So I'll be speaking today about these new constraints that we've developed on black hole natal kicks. This is Bayesian inference with sidekicks.jl. This is work done in collaboration with Pablo, as well as Alejandro Viña-Gomez, UG, and the Bloom collaboration as a whole. So I'll start by talking about black hole theory, what we know about the formation of black holes, and some of the observations that we have of black holes, the challenge that we have of constraining the natal kicks that black holes get, how we can get a solution to this challenge from inert black hole binaries, some inference that we can do on existing observed systems, and the future prospects. So I'll start with the black hole theory and observations. Now, as some of you may know, black holes come from the collapse of massive stars greater than about 8 solar masses at the end of their lives. Compact objects form from these collapse. They can either be neutron stars or black holes. And core collapse is very complex to model, but it can be reduced to a simplified mapping. And I show here a video of a 3D hydro sim of a core collapse. This is one of the state-of-the-art models. It's supposed to show a lot of the detail of the stochasticity. The specifics are not very important, but the point is that you can see it's a very dynamical, chaotic process. And so you can see during this collapse, things are really jostling a lot around. There's a lot of asymmetries. It's a very complex thing to model in detail. But for a lot of purposes, we don't need this level of detail. All we need to know is the input and the output, where the input is something about your stellar progenitor, which might be as simple as what is the core mass, what is the envelope mass. You can go into more detail if you want, but that's sort of the simplest way that we design these models. And the output is the type of remnant you have, whether it's a neutron star or a black hole, the amount of mass loss that forms this remnant, so how much of your original star goes into the remnant, and the natal kick that it gets, which comes from the asymmetries in the ejecta. So we saw that this thing was really jostling around. If you have ejecta, if you have an explosion and some of the material preferentially goes in one direction, by conservation of momentum, your remnant has to go in the other direction. So we call this the natal kick. And we really are interested in constraining that natal kick. Compact object formation really comes in 3 different outcomes. So you have a successful explosion. This is what we associate to a traditional supernova, is that bright supernova that you see in the sky. We have many measurements of these. We typically associate these with forming a neutron star remnant. So you're associated to a high amount of mass loss, or DM, and a high natal kick, because if your progenitor is, for example, 10 solar masses, and you drop down to a neutron star mass, which is about 1.4 solar masses, you have a lot of mass loss to get there. If you have any asymmetries in that ejecta, all of that mass loss combined with the asymmetries gives you a big kick. If you don't have a successful explosion, you might have a proto-neutron star formed and the beginnings of an explosion, but it doesn't quite take off. You have some of the material fall back onto that proto-neutron star, and instead you form a black hole. There's a lower mass black hole because it's a neutron star that's accreted a little bit, so it's not your full-fledged, very large black hole, but it's still it's a black hole all the same. You have a moderate amount of mass loss because you have some of this fall back onto the black hole, and you have a moderate kick because, again, you sort of imagine having the full kick on your proto-neutron star at the beginning, and then you have some mass falling onto it, and so by conservation of momentum, you have a proportionally smaller kick coming out of that. And then you can also have a direct collapsed black hole, which is associated to no explosion, right? Sometimes we see a red supergiant that just disappears in the sky, and we think that this is the end of life of a star that experienced a direct collapse. So it's not formally a supernova. It's associated to a very massive black hole, very low DM, because more or less all of the star is falling into the black hole, and so consequently you have low or no kick. There are other ways to get some small kicks, but generally we think they're very, very low. And up here in the top, we have this is the supernova remnant landscape from a population study from 2016. The different rows are different supernova models, so different ways of running this explosion. And the outcomes are colored here. So as a function of the initial mass of your progenitor, green means you have a successful explosion and a neutron star formed. Black means direct collapse into a black hole. And then the light blue ones here are your partial fallback into a lower mass black hole. And you can see that as a function of your different models. There's a lot of different outcomes here. There's a lot of stochasticity. So you have a lot of areas where you have, with slight differences in your progenitor mass, you might have a black hole or a neutron star really adjacent to each other. But through all these models, you do have this sort of central area here where you think that you start forming black holes. Maybe as you increase the mass of your progenitor, you only continue forming black holes. But we do see consistently these, what we call the islands of explodability, which is where you have sort of neutron star formation at slightly higher masses. So it's a little bit counterintuitive, but this seems to be robust and not a matter of stochasticity where some of these finer features might be. Here at the bottom is a more recent population study from Adam Burrows that looked at the detailed modeling, as we saw before, of these explosions. And for different progenitor masses, which is the different lines with the different colors, you see how the kick grows over time. So importantly, these simulations have not finished by the time that they've reported these results. You can see the kick is still growing for these largest ones. But in some cases, for these models, the kicks grow to really large values. These highest ones here are exceeding 1,500 kilometers per second. This would be an extremely large kick if we saw this. Not unrealistic. We do see some examples. The guitar pulsar is moving extremely fast. But you can see that there's also a lot that are at lower values that we might think are more typical of, for example, neutron star velocities, and then some very low ones down here. But the important thing here is that these are very uncertain from the hydro modeling. And as I said before, a lot of these simulations haven't even finished yet. So if you think that your simulation is still ongoing, it might experience later fallback. So you're not really resolving the actual kick that the remnant gets. At the end of the day, you're just seeing what it looks like at some point partway through the explosion. The important ones here for us are that these mass loss and kicks for your partial explosions and direct collapse are very uncertain, and we can't really get the answer from your simulations. They're just too complex, and we're not really there yet in the systematics to understand it completely from that point of view. So instead, we turn to observations. But how do we look for black holes? Black holes are found in a number of different ways. We can find them in isolation in rare cases. This is when you have just a black hole by itself. We also believe that we can identify them in globular clusters, where they've formed in these dynamical kind of chaotic environments. But primarily, we find them in binaries. Of course, everyone knows binary black holes, everyone's favorite LIGO source. We also have X-ray binaries, accreting systems that are producing bright X-rays, and also inert black hole plus main sequence binaries. And I'll be focusing more on these later and explaining what inert means. But for the record, we're only considering stellar mass black holes here, not your intermediate mass or supermassive black holes. These stellar mass ones are ones that formed from stellar collapse, and that's what we're interested in constraining, so we're going to ignore the other ones for now. The formation channels of black holes in isolation or in binaries. There are many different formation channels. It's hard to write just one down. I've shown here sort of a canonical illustration of a formation of a binary black hole. This is a Van den Heuvel diagram. It gives you a sense of the type of phases that a binary might experience through its life. So you start at the zero-age main sequence. You might have some stable mass transfer, a supernova in the more massive star forming a black hole, later a high-mass X-ray binary followed by unstable mass transfer, another supernova, and then your binary black hole. Now, this is one particular channel. It doesn't necessarily represent even the most common one. It's just one way to look at the types of phases we might study to better constrain the formation rates of, for example, binary black holes. Or if you just want to look at high-mass X-ray binaries, you look at the precursor phases to that one. We know that black hole progenitors, the massive stars, are primarily formed in binaries. So that helps a lot. And we know that binary interactions, particularly mass transfer, can modify the masses and orbital periods. As you exchange mass back and forth, the period will contract or expand. And the supernova itself can widen or even disrupt binaries. So when you have a supernova or a core collapse and you inject a kick and mass loss, you can induce eccentricity in the orbit. And if it's a very large kick or a lot of mass loss, you can disrupt it and have two single components. So that's maybe one way to form an isolated black hole. It started in a binary, you gave it a big kick, now it's ejected out, and you have a companion star that's maybe a walk-away or run-away star. So the formation rates of isolated black holes and black holes in binaries are sensitive to this uncertain natal kick. This is why we want to study this. It's also uncertain to other aspects of the physics, but in particular the natal kick and also the mass loss associated to the core collapse. The challenge with kicks is that we don't know how to estimate them, particularly for black holes. Now, for neutron stars, this is a much easier problem. We have on the order of thousands of isolated pulsars with measured velocities, right? Not radial velocities, but transverse velocities on the sky. Here on the top is a study from Andrei Igashev that looked at transverse velocities. The blue line here is a CDF of the observed velocities, and there's some models they try and fit to this curve. But in general, you can say that for isolated pulsars, their velocities are typically in the order of a few hundreds of kilometers per second. They're fast-moving. These are velocities that would, if it was kicked in the binary, would eject them out, which makes a lot of sense. You're giving these things large kicks, they're ejecting out of binaries, and you're seeing them with velocities that are very similar to the kick velocity, right? It's not so different the effects of the binary don't modify that kick velocity a whole lot. And so what you get is this really nice distribution of what you think most neutron star kicks look like, at least in the high end, right? Because you're only looking at isolated pulsars here, you're biasing yourself to the higher kicks. Because if you had for example, a subpopulation of lower kicked neutron stars, they would remain in the binaries and you wouldn't see them here. So this is a sense of the kicks in the high kick regime that you get for neutron stars in particular. But we don't have this luxury for isolated black holes because we only have one for which we have a well-constrained velocity. This is OB110462, where the full name is here, is MOA 11191/OGL 11462. It's very catchy. With this particular system found in microlensing, they were able to constrain the mass to something between 6 and 8 solar masses and the space velocity to about 45 kilometers per second. With some modeling, they found that the kick on the black hole might have been closer to 100 kilometers per second. Even so, this is just a single system, and it's not necessarily representative of all black holes. We also don't know where it came from, right? It's isolated now. Maybe it was one of the rare ones that was born isolated, or maybe it wasn't born in a binary. We're not really sure. But at least it's a single data point, and so we can kind of get a sense from that. But we want to do this in a more population sense. We can also turn to globular clusters. So we don't actually see black holes in globular clusters, but from dynamical arguments, you can get an estimate for the number of black holes that should remain in a given cluster. So here's a study of different dynamical models of globular clusters. And model dependent, you still get that something like 50 or 100 black holes should retain in globular clusters after some amount of time, right? And so this is telling you, even though we don't see them, that we should expect that on the order of 50 or 100 black holes are getting kicks that are smaller than the escape velocity of the cluster. Because if they were larger than that, they would escape out of the cluster and they wouldn't be retained. For escape velocities on the order of 10 kilometers per second, this gives you a sense that at least some black holes are getting kicks smaller than this value. Now, again, we're biased toward the low kicks here. We don't see the ones that are getting higher kicks, so we don't have a good sense of the fraction that are getting these lower kicks, but at least you can argue, okay, well, some of them are getting low kicks less than about this value. This is a population level estimate, not given to specific systems, so you can't say this black hole got this kick, especially because if you were to see a black hole, you don't know how much its dynamical interactions have modified that velocity. But at least it gives you sort of a hand-wavy population sense. It's also independent of the specific mass of the black hole. We can also turn to binary black holes. We have 100 or so observations of binary black holes now. Can we use these to get constraints on the kicks? Unfortunately, for binary black holes, there are many uncertainties in binary evolution modeling. For binary black holes in particular, we have stellar winds and common envelope evolution that really muddy the effect of the kick specifically. It's hard to disentangle these effects. And specifically for binary black holes, there's a study from Flora Brokegarden from a few years ago. When you look at the effect of kicks and other evolutionary parameters on the merger rate of binary black holes, we find that the binary evolution effects in particular are not so impactful on the rate of binary black holes. There's a lot of uncertainties in the evolution, but it doesn't really translate to uncertainties in the merger rate. So here what I'm looking at is, I've only shown supernova uncertainties here. The plot is much wider in the paper. But you can see that the overall height of each of these bars, which vary, each bar varies the physics that you're assuming in that particular model, doesn't really change. They kind of look the same as you move from left to right. The real height and the uncertainty in these comes from the cosmic metallicity-specific star formation rate. This is the composition of material that's forming the stars that become your binary black holes. And as Flora found, this is a much bigger impact on your binary black hole merger rate. So unfortunately, this is not really the way to go to answer questions about kicks. We can also look at X-ray binaries. With X-ray binaries, you can get a 3D velocity and try and trace back the velocity, trace back the orbit of the X-ray binary through the galactic potential. So here's a study from Pichiatri from a few years ago that did exactly this. So you take an X-ray binary, you play it back, and you say, well, we think that an X-ray binary should be born in the galactic plane. So let's play back its velocity, see how it orbits through the galaxy, look at all the times that it crosses the plane, estimate the velocity at those different times, and assuming that one of those was the point where it was born, we average over those different velocities at the plane crossing, and you get something like an estimate on the velocity that it could have had if you think it came from one of these plane crossings. This is quite uncertain, and we still have the argument that because the black hole is in a binary, the kick must have been somewhat low to avoid binary disruption. And you can get something like this. So this is for many different X-ray binaries in the galaxy. These are the sorts of constraints you get on the kicks that they get. And you can see these are quite wide. Some of them are quite low, maybe in the order of a few tens of kilometers per second. Some are quite a bit higher, closer to maybe the neutron star velocities. But the caveat with this is that you're not really constraining the kick directly, because even if you play the whole system back in time and you say, okay, well, it was the supernova happened at this crossing, we think, and it had this velocity right afterward, you can't disentangle the effect of the kick from the velocity that the system might have had beforehand. If it had any initial velocity, that's sort of added together with the kick, and so you can't disentangle those two processes. Additionally, if you have any low-mass X-ray binaries, things with a low-mass companion as opposed to a high-mass star companion, these undergoing long-term mass transfer may modify the masses and orbit of the binary quite a bit. So the masses that you see today might be quite a bit different from the ones that they were born with. And so again, you're really running into a lot of these degeneracies where you can't really disentangle the effect of the kicks specifically. So the problem is that we need a robust way to directly measure the natal kick exclusively for individual systems. And the solution comes to us from inert black hole binaries. So what is an inert black hole binary? An inert black hole binary is a wide binary containing a black hole and a massive star. And here's a diagram from a paper from Tomer Shinar on the discovery paper of a famous inert black hole binary, VFTS 243. And I'll speak a lot about this one a little later. In this case, wide means inert, means non-interacting. There's no X-ray emission, so you're not accreting onto the black hole. It is X-ray quiet throughout its life. It's too wide to be accreting. It's a newly discovered population. There's only 4 confirmed. I put a twiddle in front of the 4 as sort of questions about which ones are confirmed and which ones we trust. But it's about 4 right now. The population is growing. And the important thing here is that the lack of interactions mean the orbit has not changed since the explosion. So you don't have mass transfer, which means the masses are the same. If the orbit has some eccentricity, that eccentricity is preserved. You're also assuming in these cases that you don't have tidal circularization. So in this way, the orbit that you see today is frozen from the orbit post-explosion. In the ideal case, you have as many constrained quantities as you do free parameters. And I'll explain this in a little more detail. The constrained quantities are shown in black. So for your post-explosion system, the one you see today, we can measure, in the ideal case, the 2 masses, the period, the eccentricity, the 3 Keplerian orbital angles, so the ones that determine the orientation relative to us. And then you can also, ideally, measure 3 velocities of the system as they are today. Now, of course, the velocities are relative to us or relative to some other source. On their own, they don't tell you much, which is why we don't include them in black as true constrained quantities. In order to use the velocities, you need to have an estimate of the initial velocity that the system had, and then subtract them and get these delta velocities here, which we consider to be the constrained quantities. This is the change in velocity that the system got from the explosion. But of course, you don't have the initial velocity. You don't know what it was doing before the explosion. But if you can identify a host cluster, a birth association where the system was born, and you can identify a sample of stars or binaries in that cluster that have a certain velocity distribution, from that velocity distribution, you can draw initial velocities under the argument that the binary was probably born with a velocity similar to its birth association. And so even though this dispersion might be quite large, or might add quite a bit of uncertainty to it, at least it's a way to get an estimate on the birth velocity from which we can get an estimate on this change in velocities. Now with the 4 intrinsic parameters here and the 3 extrinsic angles there, and 3 more velocity constraints, we have 10 constrained quantities. Now if we want to estimate things about the system, we have the same 4 intrinsic quantities prior to the supernova, prior to the explosion, the same 3 extrinsic angles, so that's 7 all up. And then to describe the core collapse, you have the natal kick and the 2 angles describing the natal kick, and you also have this mass loss quantity, and you also have the periapsis value here. And the periapsis is the angle in the orbit for an eccentric orbit. It's the angle in the orbit where the explosion happens. This changes the velocity of the system, of the exploding object. It can change the outcome of the system. And so in this way, we have 12 free parameters and 10 constrained quantities. If we can additionally assume that the system was circular prior to the explosion, we can drop out one of them, right? If it's circular, we don't have to worry about the eccentricity, so we lose one of the arguments. And additionally, we get the periapsis for free. I'm so sorry, I was speaking it wrong. This is the true anomaly. I got that very wrong. The true anomaly drops out because the true anomaly is the angle in your eccentric orbit where the explosion happens. If it's a circular orbit, you're not worried about the true anomaly. More formally, the sum of the true anomaly and the periapsis become your 1 constrained quantity, so you drop from having 2 free variables to 1. And so with this one assumption of circularity prior to the explosion, you drop from 12 free parameters to 10. You have 10 parameters, 10 constrained quantities, and it's a one-to-one mapping. And in principle, this means that if you can measure all of these constrained quantities perfectly, then you can get all of these free parameters measured perfectly. I do quotes for perfectly because we're doing measurements, so it's never really perfect, and especially because you have uncertainty in your dispersion here, these things are going to widen a little bit. But in the ideal case where you can make these assumptions about the circularity and you have all of these measurements, you can actually do really well, and we'll show some examples of this later. To do this inference, Pablo and I and a few others have developed this code, sidekicks.jl. Sidekick stands for Statistical Inference to Determine Kicks on Compact Objects, and the .jl is because it's a Julia language code. So it's written in the Julia language. We have contributions from Alejandro Vina-Gomez, as well as Mats and Sukin, and a few others. Here's some examples. This is what it looks like to run input into the code. Here's some clips from the paper and some of the rotations that we do in the paper, and you can check it out here. It's open source, publicly available, so we encourage you to download it and try it out. It's a custom Bayesian inference package for analyzing inert black hole binaries, exactly the things that I just showed that we're most interested in. We allow for flexible choices of priors on the free parameters, all the ones that you want to understand. You can choose really wide agnostic ones, or if you have some intuition, you can tune those flexibly, as well as the likelihoods for the constraints. All the ones that you think you're measuring, you can apply a likelihood to those constraints and get a better sense of which ones you can measure and which ones you can't. You can also remove likelihoods if you think you can't constrain a quantity. So for example, if you don't have, for example, some velocity component in some direction, you just remove that one and you don't include it in your 10 constraints. We use rapid MCMC with the no U-turn sampler or NUTS algorithm, which may not be important for many of you, but in case you're curious, that's what the one that we use. The desired observations that we have come from the types of observations available to us. Now, in order to say anything about in order to confirm the nature of a black hole, you need to have spectroscopy. This is because if you don't have spectroscopy, you might be hiding just a dim companion. With spectroscopy, you can really rule out companions down to a certain mass and say this thing is so massive that if it was visible, we should see it. So therefore, it must be a black hole. And because we need this confirmation, we assume for all of our models that you have spectroscopy included. Now with spectroscopy, you get the orbital period, orbital eccentricity, RV semi-amplitude, which gives you a constraint on the masses, and the argument of periastron, as well as the mass of the star. I'll come back to the mass of the star a little later. But because we always assume spectroscopy, all of our models have an S appended. So the model name tells you which observations you have. Now, if you're fortunate, you might also have a resolved orbit. This is generally only available for close sources, so not extragalactic sources. But if you're so fortunate, you also additionally get the orbital inclination and the longitude of the ascending node. So we have 4 models here that have an O appended for resolved orbit. Additionally, you might have velocity constraints, which require, as I said before, you need to first identify a birth association. So you need to have the location where the system was born first. That's the most important thing. And then after that, you need to have velocity measurements of a sample of stars in that host, a reasonable sample that you think capture the dispersion that you're interested in from that host in the different directions, the different components. So you might have, just radial velocity measurements of your system and the host, in which case you have just VR. You might have just transverse velocities of your host and your system, in which case you have VT, and you might have all 3, in which case you have V3. These are all realistic situations that you might encounter. And so in that way, we have these 8 different models that capture what kind of observations you might have access to for any given system. The mass of the visible star is a particularly convoluted one. It requires extrastellar modeling. So you do need spectroscopy for this, but then you need to do some additional stellar modeling, which may be uncertain if, for example, you thought that your system interacted prior to the supernova, prior to the explosion, and you had accretion onto that star. It's now a post-accretion star. It's harder to gauge what the mass is of that star. So there's some uncertainty here. The others are generally less model dependent. Now, to verify the code, we used as a test case this famous system, VFTS 243. This should be very famous to everyone here. This was discovered primarily by KU Leuven a couple years ago, but particularly by Tomer led the study. This is a 25 solar mass O star with a 10 solar mass black hole companion. Orbital period is about 10 days. And importantly, the eccentricity is very close to 0. This is a great constraint for the kind of study that we do. It's very hard to form a post-explosion system with 0 eccentricity, assuming tides haven't affected it, with any sort of kicker mass loss. So already, that low eccentricity and the argument that it shouldn't have circularized from tides tells you that it probably did not experience a very high kick or mass loss. Nonetheless, we can still run our inference and see if we can reproduce that result. This particular system is located in the LMC, in the Tarantula Nebula specifically, so it's too far for a resolved orbit. But because it was discovered in the FLAME survey, which is a spectroscopic survey, we actually have access to all 3 velocity components. So we're using the model SV3, so no O, but SV3. And in this particular version of the inference, we've assumed that the eccentricity prior to the explosion was circular. So the system, because it's 10 days in period, we argue that it should have, we think, interacted prior to the explosion, circularized due to mass transfer, and then exploded with a circular orbit. This is there's evidence for this in the fact that the eccentricity today is 0. Again, it's very hard to get to a 0 eccentricity if you have any substantial kick or mass loss, or if you started with any eccentricity. It's not impossible, but you have to fine-tune the angle of the kick, and it's considered very rare. So there's some strong evidence for this particular system of it having circularized prior to the explosion. And what we find with our inference is that the mass loss, delta M2 here, is very close to 0. There's some support out to almost 3 solar masses, so it's not determinably 0, but it's very consistent with 0 mass loss, and also a very low kick on the order of 3 kilometers per second. Again, support up to almost 30 kilometers per second, but it's sort of dominated at these very low kick values. You can also see that the initial mass of this is the M2 here, is the black hole progenitor, is about 9 solar masses. So this is consistent again with something that was about 10 solar masses, didn't lose much mass, and has not perturbed the orbit much. We consider this a likely candidate for a direct collapse black hole because of the low kick and low mass loss. For this particular case, as I mentioned, we have 3D velocities for both the system and its environment from the FLAME survey and Gaia. So here we show the velocity distribution of both the Tarantula Nebula, this is the TMBM, in blue, and the system itself in orange. And you can see that we can constrain both of these independently. And in all cases, the system velocity, even though it's quite a bit tighter, particularly for the radial direction, it's more or less consistent with the environment. This is telling us that the velocity of the system today isn't so different to the velocity of its environment. Again, consistent with a direct collapse explosion. And if I go back here, this delta V is the change in system velocity. Again, it's very low. 3.45 is a very small difference. You wouldn't notice that on the order of these changes. If it was moving only slightly differently to what it was before, you wouldn't really see a difference with the environment around it. This is it's a very straightforward use case that we like to show off. The caveats for this analysis is that the primary must be massive and young to limit its travel through the galaxy. So if you have a low mass companion, for example, if you have a 1 solar mass companion with your black hole, it might have lived for a long time. You can't really get a good narrow constraint on a short lifetime. And so it might have evolved a lot through the galaxy, which means that it might have experienced perturbations from flybys, it might have changed its velocity direction, and things like this that can affect the inference you're trying to do. If you're trying to say that the orbit today is exactly the same as it was post-explosion, a tight constraint on the age is important. And so we prefer to have massive companions. The system also must be wide. As I said, these are inert black hole binaries. You can't do this with X-ray binaries because the change to the orbit means that it's not frozen from what is post-explosion. So if you have tidal circularization, any information on the eccentricity is lost, right? Identifying the birth association, as I said, might be non-trivial, right? In the case of VFTS 243, it's still kind of sitting in its association. If you have a direct collapse black hole, often this will be the case. It's sort of sitting in the region it was born. For many systems, this won't be the case, and it can be difficult to identify the birth association. And even once you've identified it, it might be hard to measure the velocities of that association. And in particular, this pre-supernova eccentricity is very uncertain. So for the case of VFTS 243, which is circular, it's quite straightforward to argue that it was circular beforehand. This will not always be the case. And that pre-supernova eccentricity distribution is very hard to constrain. So this is a plot from Luc Eispert's thesis from last year, where he looked at, for his sample of eclipsing binaries, the eccentricity for his period for these systems. And there's some uncertainty on the systems, but you can generally see, it's quite a nice way to show that they're mostly circular up to a period of about 10 days. And after that, they sort of rise a little bit, and you can sort of see that there's more eccentricity after about that point. So this is something of an argument to say that systems below about 10 days might be circularized through tides, and above that, they might be more eccentric. Now, notably, these are from his sample of eclipsing binaries. They're not specifically pre-supernova systems. They're not necessarily post-interaction systems. And so this is not really directly useful for what we're doing, but it gives you an idea of these sort of arguments that, okay, well, below 10 days, maybe you think it's circularized. But mass transfer will have an effect on this. This here is from a recent study from Kyle Roca and the Northwestern group that looked at the effects on eccentricity of mass transfer in eccentric binaries. So here you have your binaries starting at the crosses here, and by evolving these eccentric binaries through mass transfer and looking at the evolution of that eccentricity, in the cases where your mass transfer is very unequal, so you have a very high mass thing, donating mass into a very low mass thing, you do find the canonical story that they circularize, they shrink, and they eventually become circular, right? The blue tells you that it's becoming circular. However, they found that for systems that are more equal mass ratio, so more like 2 to 1 in mass ratio initially, the systems that are very low eccentricity to start still circularize. They still contract a little bit and circularize. But more eccentric systems, they might contract and they might circularize a little bit, but they don't ever fully become circular, right? And so this particular study used black hole accretors, so it's a little bit of a different story, but it still tells us that the narrative that many binary evolution modelers for years have been using, that mass transfer universally circularizes binaries, is probably not the case. So this shows that in some cases, you can retain some eccentricity. And there's even a third plot that I didn't show from the study here, where they go to even more equal mass ratios, so mass ratios close to 1, where they find that you can, in some cases, circularize a little bit and then become even more eccentric, or you might even become eccentric immediately. So in this way, mass transfer, in some cases, can induce even higher eccentricities than you had at the beginning of your mass transfer event. So in this way, we're sort of more uncertain than we were before. You can't rely on the fact that it experienced mass transfer to say it must have circularized. And this will be a bit of a headache trying to get a constraint on the pre-explosion eccentricity distribution. And again, I'll emphasize, because we're only looking at binaries, we're biased towards the low non-disruptive kicks. We're not sensitive to kicks that are large enough to kick the binaries apart. And so in this way, we're not really able to sample the full kick landscape, but this is a universal problem. They face the same problem in neutron star studies, but it's an important thing to keep in mind. So now I'll talk a little bit about the inference that we can do on existing systems in addition to VFTS 243. We have VFTS 812. This is a system that Kunal discovered a couple, maybe a month and a half ago or so now, and came to me. He's been looking at the same flame survey that VFTS 243 was discovered in. It's still a candidate, so it's not formally been confirmed as a black hole, but based on the initial estimates, it seems to be a 38 solar mass O star with a 6 solar mass black hole companion. Already the mass ratio is very interesting for this one. The period is about 17 days, and it's got a fairly moderate eccentricity of about 0.6. And the interesting thing about this system is when we run it through sidekicks, we get 2 competing solutions. And you can see this best in the period distribution here. So solution 1, which is the preferred one that you can see on the tops of the plots. Solution 1 has a period of about 17 days. It seems to have very little mass loss, so you're getting about a 0 in your delta M2. Again, you have some width here, but it primarily seems to be a 0 mass loss, and a very low kick of about 12 kilometers per second. We would associate this with a direct collapse black hole of a system that was initially about the same eccentricity. So this looks like a system that was at about 17 days and an eccentricity of 0.6 already, experienced a direct collapse, and did not change the orbit very much. Now, this might be the case, but we might also think that, this fine-tuned eccentricity is a little bit fortuitous. We've here used an agnostic eccentricity prior. So we've said any eccentricity in your pre-supernova explosion is valid. That's what this means here. The prior eccentricity is uniform between 0 and 1. We can choose a different prior that assumes it must have been circular. So we use a delta function on the eccentricity. And you can see, of course, your eccentricity flattens right to 0. And you find this other solution with an initial period of about 3 days here. It's really closer to 4 days. But you actually see the same solution here in the previous plot. It's just not the dominant one. When we use this circular prior, this becomes the dominant solution for the period. Now the mass loss is closer to 0.23 solar masses. Still not very much, and still consistent with 0, but you can see there's slightly more mass loss there. But your natal kick is now no longer consistent with 0. It's now very high, about 135 kilometers per second. So this would be associated to a partial fallback black hole. We have these 2 competing solutions, and it's not really clear which one is preferred. The fact that this one, the high period one, was preferred initially might just be a result of the priors that we've used. We can maybe tune that just by careful retuning of priors. So it's not really clear that this is the preferred solution. But we can use additional intuition to argue that a 6 solar mass black hole, a 6 solar mass progenitor, even if it's a stripped star, should not experience direct collapse. As we saw at the beginning, a lot of these models for your remnant landscape showed that for progenitors that are in this low mass end, it's very unlikely for it to experience a direct collapse. Not impossible, you still have stochasticity and other arguments like that. But based on this argument, we think that because we know this progenitor mass fairly well, solution 2 is preferred. So because the progenitor mass and the black hole mass seem to be fairly low, we think that this is probably a partial fallback system. Not confirmed, again, still need to confirm the black hole, but this is some preliminary results that we're very excited about. Yes, we also have HD 130298. This is a galactic system discovered by Laurent Mahy a couple years ago. This is again a 25 solar mass O star with about an 8 solar mass black hole. Typically the black hole mass is a lower limit, but these masses look a lot like VFTS 243. The period is a little bit longer at 15 days, and the eccentricity is about 0.5. And the interesting thing for this system is that no birth association has been found yet. We've looked for it. It happens to be in a very diffuse part of the sky where it probably wasn't born. It's not clear where it came from, and so we have no velocity constraints. So it's just, but it's because it's galactic. We do have the resolved orbit. So this is an SO model with no V contribution. And once again, our inference finds 2 solutions. And this can be most easily seen in the corner plot, actually. Here in delta M V kick space, you can see 2 peaks. And we associate one peak to low mass loss and a high kick. And if you move it over to this plot as well, you also associate it to a high system velocity. And the second solution is a high amount of mass loss with a low kick and a low system velocity. Again, we have a hard time distinguishing between these 2 peaks. But interestingly, both of them are away from this 0, 0 corner that you would associate to direct collapse. So even in lieu of a direct answer of saying, it's this peak or this peak, we know that this was not a direct collapse system, right? We know that this must have been partial fallback. However, if we can identify the birth association, if we can find the host that it came from, we can get a stronger constraint on VSys, which allows us to break this degeneracy and figure out which of these 2 peaks is preferred for this particular system. This is something that we've been looking into with Laurent. Here we've been tracing the orbit of the system back through the galaxy, trying to find an association that might be plausible. And as you can see, this one here, it seems to be kind of close to this RAD association. It's a little bit on the wings. We're not really convinced, so there's a little bit more work to do to verify this. But this is our approach for systems where we don't have a clear association. Try and trace back the velocity of the system through the galaxy and find one at some point in its history to get this constraint on the velocity. Again, this is a work in prep that we're very excited about. What about the Gaia black holes? Many people here are probably familiar with the 3 Gaia black holes that have been announced in recent years. They've made a lot of headlines, primarily discovered by Karim El-Badri. Unfortunately, all 3 are in very wide binaries. So this plot, which has been adapted from Karim's paper, shows many different black hole binaries in the galaxy, many of which are X-ray binaries, in terms of the mass of the black hole versus the orbital period. And you can see that the Gaia black holes are all at the widest periods that we see. The shortest one is only 100 days. Gaia black hole 3 is at a 4,000-day period. And so already it's a little bit tricky to make claims about. And you certainly can assume that it had circularized before the explosion. Also, in some cases, we don't even know that they came from isolated binaries. So there's some evidence that Gaia black hole 3 came from, is part of a disrupted stream, which means that it would have come from a globular cluster. So even if you thought, this is a valid system, we can do this inference on, we don't know that the 2 components, the mass, the star, and the black hole were born together. They could have swapped in during the life of the globular cluster. We just don't know. Importantly, all 3 also have 1 solar mass companions. And this is maybe the biggest reason why we can't use these systems, is because it's a low mass companion, so you don't get these constraints on the age and the perturbations and things like this that we really like. So for these particular systems, Sidekicks is not so useful. It violates our assumptions. However, we can use Cygnus X1, which is a very famous X-ray binary. It's the first ever confirmed black hole. It was the subject of a famous bet between Stephen Hawking and Kip Thorne. And you might be asking yourself, why can we use an X-ray binary? I said earlier, we can't use X-ray binaries because they have tidal circularization and a bit of mass transfer. It happens that this is a high-mass X-ray binary, which means it's wind-fed, which limits the amount of mass transfer that could have occurred. The reason we can use this system is because the tidal circularization for wind-fed high-mass X-ray binaries preserves the angular momentum of the system, which means that you have this relation between the period after circularization and the period in eccentricity beforehand. So even though you lose information on the eccentricity and the period post-explosion, you preserve something in the form of this circularization period. So in this way, you have one less constraint, but only one less, and you can still do something with the inference. For this particular system, a few years ago, there were updates to the distance and therefore the masses of the two components from Miller-Jones. The black hole is now about 20 solar masses, which at the time was the largest black hole observed in electromagnetic radiation, I think. Largest stellar mass black hole in EM. As we looked at the system, we found that the velocity measurements of its birth association, SIG OB3, are a bit unreliable. They're a bit older. There's some evidence that they chose systems that we no longer think are part of the association, so actually choosing the correct systems has been a bit of a struggle. But you can see that we are actually able to do this inference and find out some things about the system. It seems to have had a kick of about 15 kilometers per second. This is using no velocity constraints. So again, the SO model with no velocity. But we would like to use the velocities. And because we know the host association, we know that it's in SIG OB3, this is just a matter of measuring the velocities in the system. And we have transverse velocities from Gaia data. What we need is radial velocities, and we can do this with a Mercator campaign. So this is something that we have underway, planned for this summer. We're going to be looking at SIG OB3, particularly the OB stars, trying to identify SB1s and SB2s in this cluster to measure the radial velocities, to do this inference more carefully. And actually, I'll be doing this later this summer. So this is a picture of me at Mercator trying to measure radial velocities, learning how to be an actual observer. So what are the future prospects of this pipeline? With the Bloom survey, so this is one led by Tomer and Ug. This is the binarity at low metallicity campaign, very similar to the FLAME survey of the LMC. This is looking at spectroscopy of massive stars and binaries in the SMC. This is a plot from Tomer's official paper announcing the first reported data from this survey. You can see this is an HR diagram. You can see many of the different binaries we have here are all above about 8 solar masses. So there are many massive stars and binaries here. There's a lot of interesting science you can do. But in particular, because it's similar to the VLT Flames survey, you get radial velocities for free. So if you identify in this sample an inert black hole binary, you have your transverse velocities from Gaia, you have radial velocities from the Bloom sample, you have everything you need except for, of course, the resolved orbit in order to do this inference. So as soon as we have inert black hole binaries from this sample to work with, we can do this inference and get constraints on the kick. Because it's very analogous to the FLAME survey, in that you don't have the resolved orbit, but you do have the radial velocities. The inference is virtually identical to that of VFTS 243 and 812. You just need to use new distributions for your velocities, but otherwise it's identical. But yeah, too far for the resolved orbit, but 3D velocities are available. We also have Gaia DR4 coming out next year. I'm sure many of you are familiar with this and excited about it. The 4th data release is due mid-2026. As some of you may be familiar, Gaia DR3 was supposed to report many black hole main sequence binaries. They ended up including cuts that got rid of a lot of those, which of course affected Sutkin's PhD. This is a plot from Sutkin's paper where she looked at what they expect to get from DR4 in terms of the OB plus black hole population that you can identify with Gaia DR4. There will be many black hole plus main sequence binaries identified. A lot of them will be at lower masses, but we expect on the order of 10s to 100s of massive inert black hole binaries, exactly the things that we're hoping to look for. They might be at slightly longer periods, but many of these will still be very useful for the Sidekicks pipeline. And because it's a galactic sample, we get the resolved orbit, so it's an SO system at least. Then it's just a matter of finding the ones there where you can identify the host and getting the velocities within the host in order to get the full SV3 and one-to-one mapping that we like so much. So in conclusion, we've developed this Bayesian inference pipeline to analyze inert black hole binaries, and now extended to high-mass wind-fed X-ray binaries. This is sidekicks.jl. We've demonstrated this inference on several observed systems, highlighting the novel science cases you get when either you don't know the eccentricity beforehand or you don't know velocities of the host, things like that. And then combined with upcoming surveys, both Bloom and Gaia DR4, we expect to provide tight natal kick and mass loss constraints for on the order of hundreds of black holes, which means we get a really nice population level constraint. This progenitor gives you this kick and this mass loss to really get some nice constraints on black hole kicks, which will mean a lot better precision on predictions for black holes in binaries and in isolation. And here's a paper that is very, very close to completion. I'm really hoping to get it sent again to the co-authors tomorrow, but I couldn't quite get it done in time for this talk. So it goes. Any questions?
Thank you very much for a very interesting, clear talk. Oh, goodness, that was quick. I'll start there then.
Thank you, Reinhold. Every time I hear this talk, I'm like super excited for your work. I was wondering something. So I really do see the value of like you trying out both the agnostic eccentricity assumption and the circular. And I was wondering if by construction, are you not going to get like always two possible solutions? And do you have already in mind like any smart, I don't know, physical argument to try to find the preferred one? Like, for example, you showed that one of those preferred solutions that you found was actually saying, okay, there's no kick, so direct collapse.
Yeah.
But the core was just too low in mass, right? So that's a very smart argument to prefer one of the two. But I was wondering if there's like other things you can point at in the case.
Yeah, so that's a great question. So this one in particular that you're asking about, it seems to prefer the solution with direct collapse and no kick. And this may be a result of a funny choice of, in fact, our kick prior. So the kick prior that we use is uniform in the kick magnitude from 0 to 400 kilometers per second, and then isotropic in the kick angles. And it should always be isotropic in the kick angles. But because you're doing this uniform in kick magnitude prior, what that means is if you were to sample in the volume of kicks, you have a lot more points toward the center of that prior space. So in that sense, it might be that we're biasing ourselves toward lower kicks accidentally. So we might find that by resampling with a prior that is uniform in volume instead of uniform in kick magnitude, that we downweight that peak at 17 days and find more support for the solution with a kick. That's one approach. It is, it's messing with priors. So at the end of the day, you don't really know if you've found the right answer. You've just tuned it to the one that you want. But at least in this case, you can use this additional intuition. I think it's in general a story that you can't just run the analysis and present the answer and say, hey, we found it. You need to think about what you're doing and what you're saying. And if you're saying, okay, well, we've got a 6 solar mass progenitor that had direct collapse, that's novel and new. Is that so surprising that we trust it? That we shouldn't trust it, or is that something that we think is really the story that it's telling here?
Yeah. Oh yeah, it's really tricky. Thank you.
Yeah.
Any further questions?
Thanks, Reinhold. That was a really great talk. I was just wondering, so at the moment, the sort of global picture that I'm getting is we have detailed supernova models that, although they agree on some things, there's still plenty of disagreement, shall we say, right? Whether that's due to an inherent chaoticness between small input physics, or just that we haven't quite got the numerics down, is at the moment maybe unclear. And now we have many different observational sources that are sampling different expectations, shall we say, on the kinds of systems we should be sensitive to, in terms of the kicks, for example, like the neutron stars sampling the high kick regime and so on. So what I'm wondering is, when you backtrace to the progenitors of these systems, do we see overlap? Because if you see overlap then, for example, between these systems here, where you have, yes, you expect them to be either partial collapse or direct collapse. But if you see overlap in the progenitors, for example, of the supernova itself, then you also, with the same things that are also producing high kick systems, then are we already in a place where we can start to at least attempt to put very broad sort of probabilities on different parts of the physical parameter space for these supernova models? Or is there no overlap between the progenitor space at all in that regard? I guess what I'm asking is there a sign that it is genuinely a chaotic stochastic process, or can you deterministically predict direct collapse or not from progenitors, do you think?
So if I understand your question correctly, what you're asking is, do we have something like this from observations, where you're not looking at the ZAMS mass, but you're looking at the progenitor mass right before the explosion and the outcome that you get? This would be the ideal, right? If we can send this back to the supernova modelers to say, this stochasticity is not something that we see in the observations, or it is something that we see, and this is where you're seeing this island of explodability. This is not something we can do now because we only have the 4 systems. It's something that we would hope to do eventually with the hundreds that we're getting from Gaia and Bloom. So that is the target. We do want that's the ultimate goal, is what is this progenitor remnant mapping space. But right now, with the ones we have, we can't really make this inference.
Okay, so there's no overlap between your current isolated black hole binaries and the existing samples of things like neutron stars and other kick measurements.
With our inference, we get a nice constraint on the change in the mass and the initial mass of the progenitor. With the other methodologies, so for example, with the X-ray binaries traced back through the orbit, you can get a constraint on the velocity that it got right at birth. And so this tells you something about the combination of the pre-explosion velocity and the mass loss and the kick. All of those combined together to give you the final system velocity. But you can't disentangle those the way you can with this inference pipeline. So there may be overlap, but because of the degeneracies in the other modeling techniques and the low numbers that we have for our technique, we're not really able to say if that overlap exists yet.
Okay, cool, thanks.
Yeah.
Any further questions? Yeah, Eva.
Hi, thanks for the nice talk. So I just had a little remark that, I don't know if you saw it, but there was a paper like yesterday or today on a new inferences for the masses in Cygnus X1. And also new like parameters for the wind mass loss, etc. So I thought that might be actually quite relevant for one of the studies you're working on.
It is. I didn't know about that. Thank you.
Yeah.
I'll take a look.
It's led by Varsha Ramachandran,
Okay.
Heidelberg. Yeah. So just something to think about. And then I have two more points. Like one question is, how worried are you about triples?
Huh. I'm going to say not worried, but that's probably the wrong answer. No, they could definitely have an impact. Yes, it certainly does. If you have a direct collapse system, it probably doesn't perturb even the orbit of the triple a whole lot. If you're really having no mass loss and no kick, probably you'll still see the binary, you'll probably still see the system as a triple. For ones where you have a partial fallback and some disruption, that may cause a lot more problems. We don't have a good way to disentangle that. I would put that in the realm of, here is the answer that we get from the inference. Does this make sense? Can we argue that this is really the most sensible result? For systems that are circular and couldn't have tidally circularized, I think you're still, I think you're still safe there because it's hard to have, I think it's hard to have a circular inner binary if you have the effect of the triple further out. But you're absolutely right that this is something that we should be more concerned about and don't have a real clear way to disentangle.
Yeah, I think especially for the low mass systems, the low mass X-ray binaries or things like this, yeah, it could be that one of the formation scenarios is actually that it was formed in a triple, that it might have impacted already some of the properties of the system. So yeah, maybe just something to consider for the
That's
future.
a great point. Thank you.
Yeah, and another point is, have you considered looking at supernovae as a completely independent or like different way to look at this problem? And that is because actually from supernova theory, we expect that there is some kind of correlation between, for example, the explosion energy of a supernova and the kick velocity. And so, yeah, I don't know if anyone has looked at this before, but could you try to use, like, from a completely different way, maybe it's more relevant for neutron stars, but trying to see what kind of kick distribution you could infer from observations of supernovae?
That's an interesting question. My initial reaction is yes, I think this is more relevant for the neutron stars, but I wonder if you could do the same problem for the low luminosity supernova, the ones that you think are forming the partial fallback black holes. Do you know if that same relation exists for those?
In principle, it's the same physics.
Yeah.
So yeah, there should be some kind of relation there. Yeah, I was just wondering if someone has looked at this before, but I just thought, I mean, in principle, it's the same physics, so we should have everything should kind of align in this regard.
I would agree. That's an interesting thing to look into. Thank you.
Thank you for the great talk. I was wondering if in order to get some velocity information of let's say the bird association, you need to know from which association the object is coming from. So if it has undergone a kick, and especially if the kick is high, then it might like change its orbit in the galaxy. So how certain are you then still that it's coming from that association and not completely different association? Because
it's a great question. Well, I showed you with the one system that is clearly not part of an association, and this is the challenge that we're facing. You can play the velocity back, and because we're primarily looking at high mass systems, you still get a constraint on the age, which combined with the velocity that you have gives you a constraint on the distance that it traveled. So in that way, you can say, well, this one seems to be part of this association, but it's got an extremely high velocity. And if we actually play this back and look at the age constraint from the massive star, it couldn't have come from more than this distance. And if it was older, it maybe came from here, so maybe there's some issues with that. But the age constraint gives you a lot of benefit there by looking at the massive stars. So you can do this problem for all the systems that we have. You can say what's the velocity and what is the maximum distance it could have traveled. But in general, if it's in an association and it doesn't have an extremely high, kind of strangely high velocity, it probably came from that association.
Are there any further questions?
Great talk, Reinhold. I have a comment and a question. Which one first? Let's go with comment.
Okay.
So about Gaia Black Hole 3, it is, you said, just a quick correction. So it is now confirmed, and I think it has been confirmed for about a year now. It definitely is coming from isolated binary evolution. You can also form it in clusters, but it is you can very easily form it, especially with newer models of stellar evolution. So if you don't go with any of the old Hurley et al. Models, you can form a Gaia Black Hole 3 very easily. In fact, there are studies now that are being used to constrain stellar and binary evolution from Gaia Black Hole 3 because it's like such a good system with such known parameters and things.
Can I ask about that? Does that mean it's confirmed that it could have come from isolated binary evolution, or that it confirmed that it did? How well do we know that?
You can. The only thing I know is like you can very easily form it. Like there are many. It allows for a wide range of stellar and binary evolution parameters through which we can form Gaia Black Hole 3.
But it's still part of the stream, right?
It could be.
Okay.
I mean, it doesn't rule out. It doesn't rule out cluster evolution. It just confirms that, like, unlike for Gaia Black Hole 1 and Black Hole 2, where the likelihood of forming such a system through isolated binary evolution is very low, we still cannot explain it even with like newer stellar models. We are unable to explain their origin from isolated binary evolution. We can do it with a wide range of parameters for Black Hole 3.
I would be very hesitant to use a single system as a constraint on stellar evolution if we don't know for sure that it came from an isolated evolution. I agree with you that you can form it, but if you're using that to constrain other models, I would want to have a larger population.
I'm just saying that it is being used, but the main point is that it is like we can form it through isolated binary evolution. So if you want like that, you can use it for your study, but it definitely has a low mass companion. So
that's interesting to know. Thank you.
Yeah. The question is more about sidekicks. Can you quickly explain again that how sidekicks is working?
Yeah. So you choose your priors on the free parameters. Let me get this plot up. You choose your priors on all of the free parameters that you have in a consideration. You sample MCMC sampler through all of these. You look at which of your outcome systems are consistent with the likelihoods that you specified for your observables. And then you set your weighting on, this is the most likely outcome according to which ones are consistent with the likelihoods.
I think my question is, are you using any like binary evolution pipeline to
No binary evolution. Yeah, it's just supernova kicks.
Okay.
And so we don't even assume anything on the explosion itself. So this delta M2 is purely, you don't care what your progenitor was, whether it was a core or if it had an envelope. You're just saying it had some mass loss. You're completely agnostic to any sort of supernova mechanism.
Right. Okay, that clarifies a lot. One more question. So there are like, whenever supernova happens, there are two kind of kicks. One to the star, to which supernova is happening, but also to the system. Do you consider that? Like to the binary itself? They have a name, but I always forget it. So like there will be a kick to just that star, but also the system by itself, because it's in a binary, will get a kick.
Yeah, all of that is tracked. Yeah, so the velocity that you're seeing here is the system velocity.
Right. So does it have, again, like this is something similar to what Eva asked, like, do you think, does it have any impact on like locating your like nearby associations and stuff? Like because this seems like very important when you're trying to constrain kick velocities, right? So
I'm not sure I fully understand the question. We treat them separately. So you're applying a kick onto the object that's experiencing the supernova. That one is sampled randomly, and then you have the system velocity before and after, and so it's all self-consistent, right?
But it's dependent on the environment, right? Because this prior is coming from wherever you think that binary might have been associated.
Yeah, if you think you have two different associations that it could have come from, then your choice of association will change your choice of pre-supernova velocity.
Yes.
And so in that way, you'd have to find some way to choose between the two. There's another two-solution situation. But it would have an impact, yeah.
But has it happened yet? Like, have you had like such a system, or for all the systems you have been able to identify it clearly?
Well, except for the one that we couldn't identify any host.
Yes.
We haven't had any where there's multiple competing hosts that we couldn't distinguish. That hasn't happened yet.
Okay.
Yeah.
Thank you.
Thank you very much. I think we've reached the top of the hour, so we can thank Reinhold again.
Thank you.
Thank you very much for coming, and see you next week.